Swayam Prabha. Digital India. Educated India.
Today we are going to discuss quality control, mainly focusing on control chart. Process control. Quality control is basically a part of process control. Now, whenever we have a process, a manufacturing process, it is imperative that the manufacturing process is always steady and in a stable state. So, to keep the process in a steady and stable state, there are three functions that we need to accomplish. What are those three functions? Number one, detection in significant shift in the quality level. The second point is investigating the causes of any change detected. And the third is removing the causes by appropriate corrective actions. So these are the three steps or three functions or tasks that we need to do. Detection in significant shift, that is most important. Whenever some parameter we are trying to measure, whether it has really changed significantly or not. Otherwise, we may take unnecessary action when there is no real shift. So therefore, point number one is very, very important. Point two, investigating the causes of any change detected. We have to find out what is the cause of shift. So that reasoning we have to do, what could be the reason, and then we need to find out what is the appropriate corrective action to be taken. Now you see that second and third are technological in nature and need sufficient domain knowledge. Point number 2 and 3. This needs proper domain knowledge, but dealing with point 1, that is when the process has gone from stable level, is a statistical problem, and therefore it is to be based on sample data, as each and every article cannot be tested. If we are producing whatever I want to producing thread or producing shirts, each and every item is impossible to test. So we have to always take some sample, and based on sample results, we need to take a decision whether the process is within the permissible limit or not. Therefore, point number 1 is basically associated with the statistics. And the statistical method that has been developed to identify the significant shift in the process is known as control chart. That is what is control chart. Now, variations we have already discussed. In any production process, variations are unavoidable, and sources of variations could be either random or it could be because of some assignable reasons. Some reasons which are random in nature, and there are some reasons which are assignable. That is, we can find out that there is a specific reason behind this, and we'll be able to, maybe we'll be able to regulate it or control it. Random variations could be very small, but could be intermittent in nature, and very little can be done about it. Assignable variations, generally they are large, and we have some control on this type of variation because of this type of reasons. So examples, differences between machines and operatives that can lead to variations. Operator to operator, the skill of the operator may differ, and therefore there could be some variations in the quality characteristics of the product. Every human being, every operator is not equally skilled. Similarly, there could be machine to machine variations. We may have a set of sewing machines or set of draw frames or set of carding machines in an industrial shade, and there's always a chance that there is a machine to machine variation could be there. But variation due to machines or due to operatives, they can be minimized. Similarly, there could be variation in the raw materials, the input material which is coming. So that material can also vary in its characteristics. However, we can exercise some control on this also. So therefore, we say that there are some assignable variation on which we have control, and there are some random variation on which we do not have control, like change in relative humidity from place to place within the shade, or sudden change in voltage. So there are certain, this kind of random variations could be there which are difficult to control, and therefore we generally leave it, because we know that we will not be able to control that. The assignable variations they remain permanent, and they remain over a long period of time. So control chart is designed to detect these assignable variations. That is, we have to detect it. Unless we detect it, we will not be able to really take the corrective actions. We will never know whether the process has gone out of control or not. See, the random sources of variations are present only, if the random sources of variations are present, and if observations of the process is made sequentially with time, these observations will show a systematic trend, will show no systematic trend, it will not show any systematic trend, and run above and below the mean level. That is, if the variations are quite random in nature, and if we make some observation about the process or about the product that is coming out of the process in a sequential manner with respect to time, then we will find that the observation will show us that there is no systematic trend. And if we plot the data representing a particular characteristics of quality, we'll find that these data points are falling above and below the mean level, that is, the data will behave in a random manner. There is no pattern that we will observe in the data points if we plot them sequentially on a graph paper. Such data will conform to some statistical pattern. So there is a statistical pattern that can be observed in this random data points. Example, number of defectives found in random sample collected from a stable process will tend to follow binomial distributions. Similarly, the means of samples will always follow normal distributions. If we take samples and find out means, then if I plot these means sequentially, then we'll find that these means will follow normal distribution, because we have already studied earlier that sample means follow normal distributions. Similarly, defectives found in a sample will also follow what is known as binomial distributions. So this distribution we have already studied earlier. Now, if the process is inspected regularly, the variation it shows can be compared with allowable random variations. So whatever variations I am getting in a process, I can compare it with some, we can have some benchmark, and then we compare against that. After comparing, if the observed variation conforms to the exact expected random variations, the process is considered to be stable. That is, the variation that we observe, or that is, we do some calculation to find out what is the variation in it, and if that conforms to the expected random variations, then we'll say the process is still stable. Some variation is always expected because of randomness. That will be always there. We can't help them. So based on this background, we can now understand what is the general principle of a control chart. Now what we need is to know whether there is a significant departure in the process or not. That is the main objective. As long as the data points may be random in nature, that does not mean the process is not stable. These points should not cross a certain limits. And we want to find out whether the departure is too much or not. That too much means whether it is significant or not. So this can be done by hypothesis testing, which we have learned already. So null hypothesis would be the process is under control. Alternative hypothesis will be just opposite. The process is not under control. So these are very simple statements now. Suppose a sample of size n has been taken from the process. Okay, and a parameter theta is measured or it is calculated. So there is a process which is going on, process of manufacturing fabrics. It could be manufacturing yarn, it could be manufacturing some apparels, whatever it is. And let us take that we take a sample of size n and a parameter theta, whatever is the parameter, is any arbitrary parameter theta is measured. So theta could be number of defective garments in the sample. That if I choose, let us say n is 100, I found out in these 100 shirts, how many shirts are defective? Maybe I get a value 10. Again I choose after some time another 100. And then again count how many defective shirts are there. This time a value may come 8. So this way, if I keep taking samples of 100 shirts from the process line at a certain interval, maybe shift-wise I choose, then I can get some data that what percentage of shirts are defectives or the garments are defectives. So theta could be proportion defective garments produced by the process, or it could be defects in the yarn per 1000 meter. How many defects? Defects in the yarn is thick place, thin place, neps. How they are varying from 1000 within 1000 meter, how many defects are there? So we keep counting the defects over 1000 meter of yarn, and we do it over a period of time and find out what is how the defects are distributed, whether their number is more than expected or not, things like that we can do it. Similarly, it could be the count of yarn. Maybe we are trying to produce a count of 30 texts, so we keep taking samples every shift, or maybe at an interval of 4 hours, whatever that can be decided by the manager. And if we do that and keep a record of that, and then that could be also a parameter of the process, that is count of yarn. So theta could be anything. And if the null hypothesis is correct, the pattern of variation of theta will be known. If it is correct, then the way the theta will vary will be known to us, because we know the some parameters of yarn, fabric, or defects, how do they vary, which kind of distribution they follow. That we have already studied and we have learned them. So you know that faults will be at that level, it will follow this kind of distributions. So the pattern of variation therefore will be known if the null hypothesis is correct, that is, the process is under control. Let us say the distribution of theta, that parameter is shown by this graph. This is distribution of theta. This is distribution of count, maybe. This could be distribution of whatever. Could be strength of yarn. So let us say this is a typical distribution of theta. If the process is under control, most of the observed values will be close to the mean. So look at this. Theta is this side, and on the y-axis we have frequencies. Now, or it could be relative frequency. And here we have a point, and there we have a point in the graph. This is the standard deviation of theta. Here the mean is lying. If the process is under control, most of the observed values will be close to the mean. And most of the data points, that if we keep collecting data of theta, we'll find most of them are falling here only, in this region, from here to there, with different relative frequencies. If an observed data fall in one of the tails, or if an observation fall in where? In the tail. There are two tails. This side is still one tail. From here to there is one tail. Then we will have doubt about the truth of the null hypothesis and consider adopting alternative hypothesis. if I find some data here, here, then that is what will come to our mind. We will have doubt because we expect the process is stable. Most of them should fall close to the mean. Now, point is, how do I define the tail? The tails are defined on the basis of significant level. That is, whether we want 5% significance level or 2% significance level or 1% significance level. This is all decided by the level of significance. So the tails corresponding to an area equal to alpha by 2, and we get two limits of the tail, one of them known as upper limit and the other one is known as lower limit. Tail, what is this tail corresponds to an area which is equal to alpha by 2, where alpha is the significance level. And therefore we go to the right hand side and left hand side, and this area is alpha by 2, this area is alpha by 2. So they are equal on both sides. Now we apply the following rules. If an observed value of theta is such that theta lying between upper limit and lower limit, UL and LL, the process is assumed to be under control. As I said, if the values of theta lying here, then we say the process is under control. Otherwise, if it falls there, then we can say the process has gone beyond control and some kind of corrective actions we may need to take. That is the conclusion we'll draw. So this is the rule that we can apply, and the rule is based on the level of significance. Now what I can do, I can turn the previous figure by 90 degrees. That's what we have done in this case. As you see, look at the figure. Same distribution figure is turned by 90 degrees. And we extend the control limits to the right. Upper limit and lower limit. It was here. We extend this line on the x-axis. And the lower limit line also on the x-axis. And now if you look at this graph now, where these dots are representing the data, the value of the parameter theta as a function of time. X-axis is basically time axis. And these are the points are indicating the values of the parameter theta at different point of time. So this is the first reading, this is the second reading, this is the third reading, this is the fourth, this is the fifth, sixth. Like that it is going on. This is 7, this is 8. At equal interval we must plot these points. And you get a chart. This chart is known as Schwartz control chart. This is what is Schwartz control chart. So now the inspection results are plotted at regular interval, and as long as points lie within these two limits, upper limit and lower limit, they are basically upper control limit and lower control limit, the process is assumed to be under control. So these two lines are indicating that as long as the points are lying within these boundaries, we'll say the process is under control. We cannot expect all the points to fall on the mean value on this center line. That will never happen. That is something which is not possible. When a point falls beyond the limit, then only there is an alarm in our mind that the process is considered to be out of control now. Like here, the point number 8, shown by the red dot. This has gone beyond the upper control limit or UL, and therefore we can say the process might have gone beyond control, and an investigation is initiated to find the cause of this. And maybe after taking corrective actions, the subsequent readings are falling between the two limits. So we can say that whatever corrective actions has been taken, this corrective action has given the right result. Therefore, 9th point onwards, 9th, 10th, 11th, 12th, 13th, like this, these points are falling between the limits. So we can say that the process which went out of control due to some reason, that reason the engineer who are working there could find it out and set the process right, and now the value of the parameters theta is falling within the two limits. So process has been brought back under control now. Now point is these limits that we have specified, which is based on the significance level. Now we have limits which are known as action limits and warning limit. What is action limit and what is warning limit? We are going to discuss. First of all, action limits. The choice of alpha generally is 0.002 or this is the value of alpha, 0.002. If the distribution is normal, the position of control limits will be standard normal variance corresponding to the tail area alpha by 2, which is equal to 0.001. So let us read it again. If the distribution is normal, distribution of the points are normal. Suppose this is the distribution of mean values of yarn count, which will follow normal distributions. If distributions are normal, or for that matter, the irrespective of the distribution of the parameter, whether it is normal or it is binomial or Poisson, it does not matter. If we take samples of a certain size, which is 30, then the mean values of those samples will always follow normal distribution, which we have learnt earlier. That was discussed long ago in some lecture, that the sample means always follow normal distribution irrespective of the distribution of the parameter or the variable. The sample means will always follow normal distribution. Therefore, the distribution, if it is normal, the position of the control limits will be standard normal variate correspond. That means standard normal variate is what? This is the Z value. The standard normal variate is basically Z. So its value of Z corresponding to the tail area alpha by 2 is 0.001. If we look at the Z table, and if you find out corresponding to 0.001, this value alpha by 2001. What is the value of z? So z 0.001, you will find the figure 3.09, and the control limits therefore will be what? Mu theta plus 3.09 sigma theta. The value of z is 3.09, and therefore the limits becomes the mean value mu of theta, the parameter theta in which you are interested, plus 3 times sigma theta, standard deviation of theta. And warning limit is based on maybe alpha equal to 0.05, and when alpha is 0.5, the alpha by 2 will be 0.025. So for alpha by 2.025, z 0.025 is going to be 1.96. That also you can find out from the table, and therefore the control limits will be mu theta plus minus 1.96 sigma theta. So this is what is known as warning limit, this value. From this value we can draw a line. I will show that, it will come into the next page, and this will be my action limit. So warning limit means it is a kind of warning. We have to keep watch on the process, because there is a possibility now that by the time I collect next data, there is a chance that the data point might go near the action limit, or it can cross the action limit. So we call it a warning limit. Now the control chart looks like this. We have removed that distribution graph, so there is no need that. We have a central line where the mean is existing, mu of theta, and then there are two blue lines that you see. One is upper warning limit and the other one is lower warning limit, and where they are located, mu theta plus minus plus, this will be plus, sorry, not no minus here. Similarly, this should be also only minus this side. So this is here plus 1.96 sigma theta and mu theta minus 1.96 sigma. So they are equidistant from the central line with these two blue lines, and that distance is 2 times standard deviation. 1.96 is close to 2, so we can write roughly it is 2 times standard deviations, and the warning limits also are shown by the orange color lines. And if you look at this value, this is mu theta plus 3.09 sigma theta and mu theta minus 3.09 sigma theta. That is upper action limit and lower action limits. So upper action limit is close to, you can say, 3 times standard deviations, and the warning limit is 2 times standard deviations. So one is 2 times standard deviations, they are away from the mean by 2 times standard deviations, and the other one, action limits, are away from the mean by 3 times standard deviations. Roughly there are 3 times and 2 times, but the exact values are 3.09 and 1.96, because that is the z value we will get if I keep alpha at 0.002 and alpha for the warning limit at 5% or 0.05. A control chart is a simple graph with time on the horizontal axis and quality characteristics in the vertical axis, that is y, along with the control limits. That is what a control chart is. So this is that the diagram that you see now, this is the control chart. This is a chart without any data points. A control chart, therefore, is a continuous graphic indication of the state of the process. State of the process. So that is all about the control chart basics that we have learned. Now we are going to take up one example. Now the data, you can read this example number 1. Over a period of time, daily samples of size 200 were chosen from a production line. On a daily basis, we are choosing the samples. These may be, let us say, t-shirts, or these may be socks, anything that we are manufacturing. And the number of defectives on each day was counted. And the results is given in the table. So day-wise we go, first day, second day, third day, fourth day, fifth day. This is maybe the first day of the month, and then we go up to 20th day of the month. We start here, and the corresponding number of defects each day, the process producing, they are all listed here. First day the process produces 7, second day 8, third day 1, fourth day 5, fifth day 0. No defects were found. So like that, this is a number of defectives are shown here. They are random in nature. Now for this particular example, we need to find out what are my control limits. For that, what we need to do, first of all, we have to find out what is the value of mean. So mean is, in this case, very simple. You simply add all those defects, their numbers. I am continually, so these are the values, and how many days? 20 days. So I divided by 20, I get a figure 5. So 5 is the average number of defects produced per day. That is the mean value of defects produced per day. How much? It is 5. That is the average. Sometimes it becomes very high, 15, and sometimes it becomes very low, 0, or even sometimes 0 or 1. So these are the values I am getting. So we are getting a range of values starting from 0 to 15. So the mean is this. Now the question comes, what is the standard deviations? You have to be little careful about what will be the standard deviation for this data. This is a defect data. So that is the clue. That is a defect data. So if it's a defect data, then how to find out the standard deviations of defect data? The simplest way is defects follow Poisson distributions. And if it follows Poisson distributions, then for Poisson distributions, standard deviation is root over mean. So what I should do? This is also you have learned while we were discussing the Poisson distribution. If I know the mean of Poisson distributions, standard deviation will be root over mean. Why it is Poisson? Because defects per unit area, per unit length, they always follow Poisson distributions. And hence, in the present case, the standard deviation is going to be root over 5, 2.236. That is the standard deviation. You need not to calculate the standard deviation following the traditional rule. There's no need to do that. Because we know it is a Poisson distribution, so straight away we write standard deviation is root over mean, and therefore sigma is root over 5, 2.236. So I know what is my sigma. Once it is known, rest steps are very simple. Warning limit mu plus minus 1.96 sigma. So mu value is 5, 1.96, sigma value is 2.23. So it will be 5 plus minus 4.37. That is be my warning limit. So mean is 5. On the positive side, it can go 9.37. Negative side, it could be 1.37. That is the range in which the warning limit is going to lie, almost 1 to 9. And if we go to the next actual limits, it will be 3 times sigma. So 5 plus minus 3.09 to 2.23 to 5 plus minus 6.89. That means on the higher side it can go 11.89, so close to 12. And on the lower side, how much it can go? 5 minus 6.89. It is becoming negative. So negative value of actual limit, obviously false cannot be negative, so it could be considered to be 0. Therefore, Poisson distributions there is a wide variations, and on the higher side it can go up to 12. But the lesser the fault, the better it is. So lower values. Actually, in this case, we are not so much keen to know what is there any warning limit or action limit for the lower. For this particular case of defects, the lower the value, the better it is always. So here it will be more interested to know what is my warning limit on the an action limit on the positive side. If the values are coming too low, you have to think whether your instrument is giving right results or not. This is something will be, I should not say it is impossible, but at times we may get value 0 also. But we have to be that time be little careful that whether the instrument is giving proper results or not. So we can find out this way what is the limits, warning and actual limit. If I go for NEPs, these values will be very high. NEPs also, NEPs per unit length, if we go, we can also find out how many NEPs are there per unit length. And that also will follow Poisson distributions. And we are going to discuss one more example. A non-woven fabric manufacturer wants to produce fabric whose thickness specification should be mean is this much, 0.150 centimeter, and standard deviation is 0.002 centimeter. So specification is given for the fabric. Use this specification to calculate the center line and 3 sigma control limits for sample average. 3 sigma control limits for sample average. Why the average is determined on the basis of 5 readings. The average is based on 5 readings. So this is what is stated here. And we have to find out what should be my central line, that is the mean value, and what are the control limits, that is 3 sigma control limit. It is already given, so need not to calculate the warning limits in this case. The solution, if we discuss now, First step is there is no data table, so there is no need to calculate mean. Mean is already given. So whatever is the mean of the population, which is 0.150 centimeter, 0.15 centimeter, that basically means 1.5 millimeter thickness. Not one fabric we have to manufacture. Therefore, whatever is the population mean is given, the population standard deviation is also given 0.002 centimeters. So we have to produce this fabric with a mean thickness 0.15 centimeter and standard deviation. The variation which is allowed is 0.002. But we have to find out the control limits based on sample average. So we have to find out what is the mean of sample averages. So mean of x bar is the sample average. The sample average is samples. How many readings are there? 5 readings are there. So this is not going to change. Whatever is the population mean, that becomes the mean of sample means. So that this is not going to change. But sigma x bar standard deviation is going to change. It will be 0.002 by root over 5 minus 1. Because number of readings are less. So you have to degree of freedom should be 5 minus 1. If it is 30 or more, then we could have gone for whatever number, so 30, 40, then we need not to bother about this. Therefore, 0.002 by root over 5 minus 1 gives you 0.001. Root over 4 is 2, so the numerator is divided by 2, we get the figure 0.001. So you know both now. So now next step is extremely simple. 3 sigma limits is 3 sigma x bar. So this is 0.003. And next, so upper control limit is the plus 0.150 plus by 0.003, so B gives you 0.153. And the lower control limit is minus 0.150 minus 0.003, which is 0.147. So this is how we should do it. So therefore, if I draw this line, this is my mu x bar, which is 0.150. And now I have here and here, this is 0.153 and this is 0.147. That is when the plot is x bar. This is actually mu x bar. Because I am plotting the data, not the exact individual values data, but the average of 5 readings always. So these are basically average values. The original for the population, this value is 0.150, but if I multiply the standard deviation 0.00 to 3 sigma limits, it will be 0.006. That means 0.150 plus 0.006, which will make it 0.156. This, for respect to population, would have been here, and this value would have been also less. It would have been this 156, and this would have been 0.006 less than 0.150, so it would have been 0.144. I can put 0 value sum. So this is for the when I am thinking about the population, trying to control the populations. But if I am plotting in terms of sample means, then the limit is between these two. The mean must lie between these two. That is because this is the control chart for sample means. So this is what we are keeping our discussion limited to the origin of, say, the control chart, how the control chart came into the picture, what is the reason behind this. We want to keep certain process under control, and to keep it under control we have to monitor the process time to time. Monitoring is in terms of measuring something, some parameters. If we have to measure some parameters, we measure those parameters, and then we have to decide whether the parameter that I am measuring, that measured value, if it crosses certain threshold limit, then only I should say the process is gone wrong, I need to take some actions. So this decision making, that when the process has gone beyond control, or when the process demands some action, this is what is decided by applying some statistical principles to find out what is the value, that is 3 sigma value or 2 sigma value from the mean value. So there is a logic behind this, and is all based on some statistical principles, that is significance level, which most of the background has been already given to you in the previous lessons. So you can say that it is an extension of whatever you have learned earlier, simply applying that in order to keep certain process under control. With this, we close today's discussion, and thank you. We'll continue with this control chart. There are some more things we need to learn, so we'll gradually learn them. Okay, thanks.